Hey, hi all. Welcome to this meet by deeplearning.ai. It's an Pioneer AI Kolkata meet on NLP and other features as well. We have an exciting lineup of speakers for this event today. First, we'll have an introductory video by Dr. Andrew NG, and he will take us to a tour of the deeplearning.ai system. Then we'll move ahead with Anubhav Singh. He is an author, he is the DSC lead, and also an Intel software innovator. Then we have Charmi Chokshi with us. Uh, she is a Google developer expert uh, for machine learning. And then we have Souradip Chakraborty with us. He is also a Google developer expert for machine learning. So before we move ahead, let's share my screen and share with you a message from Dr. Andrew NG.
Hello, deep learners. I'm Andrew Ng, founder of deeplearning.ai, and excited to welcome you to our global deep learning community. I know that many of you are here today because you want to break into AI and build your career. I hope that being part of this community will help you to do so. To give you a proper welcome, I'd like to show you around our offices and meet some of the teams so that you can see where a lot of
Oh, hi, Andrew.
do you want to tell our friends at Pine AI what you do at deeplearning.ai?
Sure. Hi, everyone. I make articles and other media that help people learn about AI and help them understand the huge impact that AI is having in the world. Today, I'm putting together the next issue of The Batch, our weekly newsletter, and I'm looking for the biggest stories of the week to keep our readers informed.
What's been the most surprising thing you've run into working on the batch?
How much is going on in this field? There's never a dull moment. You know, you might think from the outside that machine learning engineers really understand everything about AI, but nobody understands everything about AI because this field is just coming to life right before my eyes as I put this thing together every week.
All right, I know you're really busy, so I'll let you get back to it.
Thanks. See you later.
Let's go meet Jian, who helped me create the deep learning specialization. He's working on an exciting new project. Hey, Jian. So, do you want to tell the people at Pine AI what you're working on?
Yes, sure. I'm leading a project called Workera, focusing on helping people get offers in AI and navigating their career by testing their skills, preparing for interviews and certifying them, as well as matching and referring them to good jobs in AI.
That's really cool. And what's the most exciting part of your day?
You know, the AI field is new, organizations and jobs are still misunderstood. So I'm excited to help people understand what different types of jobs exist in the field, what tasks they will work on, and what skills are needed to achieve those tasks.
I think that's really important work. Well, it's nice chatting. And now let's go chat to Hotel, who is on their product team.
Hey, Andrew.
Do you want to say hi to our friends at Pine AI and let them know what you're working on?
I would love to. Hi, everyone. I lead the product team in deeplearning.ai, where we create AI education content accessible to people all around the world. People like you.
And what are you most excited about right now?
I am so excited to see our community grow and to see how eager people are to learn more about AI.
Thanks, Hotel.
Thanks, Andrew.
So, as you can see, our team is working hard to support you and help you learn. It's never been easier than before to break into AI. So, if you want to build a career, you can leverage online resources available, including open source code, datasets, papers, and online courses like a deep learning specialization on Coursera. as part of this journey, I hope you get your hands dirty too. Don't be afraid of diving in to build your own project, or go ahead and try to replicate a research paper that you're excited about. One thing that I've seen help a lot of people succeed is if you can build a community or find a community of fellow deep learners you can meet with and study with on a regular basis. In fact, I hope that this Pine AI meetup that you're at right now will be a good place for you to meet these people. I hope you enjoyed the event today and that you learn a lot both from the talks and from each other. And once again, welcome to the deeplearning.ai community.
So, did you enjoy the video? Okay, I see some noises were coming, but later it was fixed, I guess. So, yeah, fine. Before moving ahead with our next speaker, Anubhav Singh, I would like to remind you all that we have a special post-event survey that would be sent to your email ID from deeplearning.ai. On filling that post-event survey, you would get 50% off on any course from Coursera that you pursue from deeplearning.ai. So without further ado, let's move ahead to Anubhav Singh. As I said, he is an author, he is a DSC and SSC lead, and also an Intel software innovator. And on a side note, he has also offered a copy of his book uh, that he has co-written with another of our previous speaker in our previous uh, Pi and AI meetup, Shayok Paul. Shayok Paul is also in the chat now. I can see. So, hi Shayokda. So, let's move ahead with him.
Thank you for the introduction, Rishiraj. And hi, Shagda. I see you there in the chat, and that's amazing to have you here. Um, I won't waste a lot of time because I have a lot of code to do today, and hopefully, all of you will like it. It's pretty basic code, and whatever I'm going to talk about is going to be very introductory. There's not going to be a heavy uses of scientific terms which might scare you. There will be just some basic terms about NLP, and I'm sure you'll enjoy this short and like quick session. So, Rishiraj, can you please bring up my slides? Thank you. So, starting off with the topic, building your own SentiBot, right? So, a quick introduction. Yes, I am Anubhav Singh, and I do a few things, and I'm associated to a few prestigious organizations. And now coming to why the topic, right? This is probably the one thing which I love talking about the most. And the reason why we are going to talk about to building your own SentiBot is because knowledge isn't power until it's applied, right? You might know a lot of things, but unless you're applying it, you're not actually using that power that you have got from the knowledge which you have earned with by your hard work. And if you want to summarize this, because this is like a traditional thing which I like doing about codes, and this is what, right? So when you create a Twitter bot that replies with empathy, that's actually the moment when you say knowledge is power. So what are we building today, right? A very quick gist of what we are going to build today. We are going to build a Twitter bot that whenever you tweet with, say, I'm going to run it on my own profile, and whenever you tweet saying hi Experian blah 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 blah, it's going to reply on that tweet whichever you make to my account, and it will reply on the basis of the sentiment that your tweet has. Like if you tell me that hey, you did a very nice job out there, then that's a positive sentiment, right? And I'll probably reply as thank you, or maybe like I'm happy that you liked it, right? So that kind of answer should be coming out from the bot. And if you just say things like, hey, that was not cool, or you should not have done that, that was very bad, then the type of response that we expect here is something like, hey, I'm sorry, I will not do that again. Or maybe some kind of defense, which obviously this bot won't be able to do yet because it's going to be pretty rudimentary. I'm just going to keep it very simple, very bare bones, so that you can follow it very easily. And I'll also be sharing the code repository so that, and while you're going through it, you will probably realize that the code is very simple to go through, and you can probably replicate it like within under 30 minutes. Like it's going to be faster to replicate than it's going to be to create it here in the session. And finally, yes, we'll be deploying it on a cloud server. The reason why we're doing that, because I want it to be available for some time, probably like maybe one day, and you all can try out, just sending me some tweets, and let's see how well it replies. So what are you going to need? You're going to need a Twitter developer account. You might not have it, I know that. And in case you have it, well and good. If you do not have it, then it's going to take a bit of time. So I don't suggest jumping to Twitter developer website right now, because you'll have to fill a kind of lengthy form, and it will take a few days to get it activated. You can instead use alternative libraries like Twint, though I'm not allowed to recommend it. So it's like up to you whether you want to use Twint or not. And then you'll need a cloud VM, because you'll have to deploy it on a cloud. And Lambda isn't going to work here because there's a continuous polling that's going to be happening. Lambda or App Engine or Heroku are not going to help you out here. You'll need a proper cloud VM. And you'll need a basic knowledge of Python 3, because our code is going to be in Python 3. And then you will need a nice code editor. The code editor could be anything. And finally, you will need motivation and probably a little bit of help, which I'm going to give you right here. So very quick revision of some of the concepts around NLP before we begin, just to set the tone of this today's entire event. Because there will be a lot of terms which I may not be using in my session, but the other speakers today may be using these terms, and you might feel, good to know them beforehand. So, first of all, talking about corpus, and you will actually come across this term a lot while you are studying NLP. Probably after like every one page, you will come across corpus, or maybe like every 10, 20 lines. So, a corpus is basically a collection of writings from any given author, or from a genre, or maybe any one single source, right? So, this could be like authors, publishers, type of writing, a range of time in which things have been written, or maybe other features associated with the text which have been written, maybe a certain language. So a corpus could be defined on any of these parameters. For example, the collection of Shakespeare's works, or the threads on any forums like Stack Overflow, they are all eligible to become considered a corpus. Finally, coming to part of speech. So part of speech basically, when you decompose a sentence into its constituent words, and you perform the analysis of what contribution each word makes to the sentence, then you are actually trying to perform or recognize the part of speech that particular word is in that sentence, right? For example, if you take the sentence Ram is reading a book, then Ram is a noun, and reading is a word of action, a verb, and book is the object, right? It's also a noun. And in English language, we have typically 8 parts of speech, like rule 8 words, 8 types of parts of speech. And in case you want to know more about them, you can visit these links, partofspeech.org. It will give you a very nice introduction to what parts of speeches are. And you can test out part of speech tagging of your own sentences at the second link on the slide. You can just go there and put in any test sentence of your choice, and it will tell you which parts of speech it has been able to recognize in that sentence. Now coming to tokenization, and tokenization is like very simple stuff. It's just breaking down larger pieces of text into smaller pieces of text. So pieces of text could be like from the very elementary level, they are alphabets, and then you go to words, you go to sentences, and then you go to paragraphs, finally documents, and then you might just go into a collection of documents. So wherever you are breaking down stuff, it's tokenization. And stemming and lemmatization, I'm not going to go very deep into their differences, but in short, stemming is a rule-based process, and it might sometimes produce words which are non-existent in the human dictionary. And if a human reader is looking through a stemmed text, then he might not understand what it's being said. Lemmatization, on the other hand, is taking into consideration the context of where that word is in the sentence, and it produces root words which actually exist in the dictionary most of the times. So if you do lemmatization on a sentence, then it's most likely that you will understand whatever is being done there, right? Whatever the output of lemmatization comes out, you will probably be able to read it and understand it. So that done, I think we are good to go and start coding. So Rishas, can you please bring up my other screen? Thank you. Let me zoom this very quickly. We don't have an option to zoom it. No issues. Cool. So let us start with the coding part of it. And let me very quickly create a first folder, and let me name it Senti. It could be anything of your choice. And once I've created Senti, let me go into it. And I'll create few files here which will get us started very quickly with building the things. So I'll create a file called bot.py. I'll also create a file called .env. We'll store our environment variables here, which are basically the API credentials which we are getting from Twitter. You don't want to leak them at any point of time. And if you're pushing it to GitHub, if you don't have it in a hidden file, then it's going to appear on your GitHub, and people might just take advantage of it. The next thing that we want to create is config.py, so that we can fetch the environment variables from and we can start the initial authorization and other settings with the Twitter developer APIs. And you might want to have other files like readme and license and gitignore and stuff like that. So let me quickly come to the code part, right? So coming to the first file, the config.py, and something tells me you're not able to see it very clearly. I'll try to zoom it in. I think that should be good. Yep. So the first things that you want to do is you want to import the libraries, whichever are required, and then you want to set up a logger because we are going to do some basic logging sort of, and then we are going to create, we are going to pull out the environment variables which you're going to set in the .env file. I have created a sample for you here. This is how your env file should be looking like. You should have a consumer key, you should have a consumer secret, you should have access tokens and access token secret. Now, how you're able to get this, let me quickly go to developer.twitter.com. I've already applied for my developer account and I've also got it approved. And you will have to go to apps. You'll have to create one, and I have created a app here. And if I click on details, then you can see that I have some keys and tokens. So you're free to take a look at these because I'll later on delete all these keys. So it's not, I think, anyway going to affect me a lot. And you just don't want to share it out in the public. And if I'm putting it here in the video, then I absolutely know that there are no issues with this. Yes, Sublime's gone. I was a Sublime user for a long time, but I have switched to VS Code, and I'm loving it. It's great for productivity. Yep. So this is how you can get your access keys and customer keys. So you'll have to set them up in here, and if you just put an export uh, keyword here in Windows, it might be different. On Linux and Mac, export will work. You can just do a quick source.env, and that will source all the that will set all the environment variables into your environment, and you will be able to use them in your scripts while that environment is active. And you will see here I actually have my Anaconda active, and it's actually kind of recommended to have Anaconda on or Miniconda on your server, because then you will get a lot of libraries which you might otherwise have to install manually. It keeps your requirements.txt smaller, and that's actually a good thing to have. So coming to config.py back again, once we have said this, we will do a quick authorization with the Twitter API endpoints. And once we have verified the credentials, we will actually either raise an error, or else we will put a logger info that we have authorized successfully with the server. And we will return the, oops, yeah, we'll return the API object, right, which is the API object which is authenticated with the backend, so that we can quickly make the API calls using this particular object. We can also use config parser. Yeah, there are actually a number of ways how we can do all these things, and it's probably just up to the developer and the requirements. Because here I just wanted to keep it very simple, which is why I did this. There might be simpler ways. I do not say that this is the best way, but this is one of the ways which I found very quick. Because developing this entire code actually took me like 1 hour, so probably you can do it as well. Now coming to bot.py, right? The first things that give me a minute. I'm having some issues here. So the first things you want to do is you want to import your required libraries. And this is how you import them. And then you might want to set up a main function, the function which will run when your script starts running, when you do a Python space bot.py. So you will first call the create API method from config, which we just created, and we will fetch the last tweet from the user's timeline, right? Why we are doing this? Because we don't want to fetch, like, we are at one point of time in the code, we are going to fetch all the tweets in which a particular user has been mentioned, and we don't want to fetch them from the start of the time, right? We want to fetch it from a certain time, since maybe the last time since the user tweeted, so that we don't keep on duplicating everything. We don't keep on just making duplicate replies on single tweets which are made to us. And that's why fetching the last tweet is the easiest and best option here, so that you can just start replying on the future tweets, right? You don't reply on the tweets which are in the history. And once we have fetched the ID of it, we will set the since ID. So if you go to the Twitter developer docs, you will see that since ID is used to define that from which ID onwards you're going to fetch all the tweets, so that you don't fetch, you don't end up fetching all the 1,000 tweets that a single user might have made, or maybe sometimes in millions. Once we are done with that, we are going to create a logging, because we are going to need a lot of logging in here. And then we just make a log that we are starting with. Just make it small. Yeah. So we make a log that we are going to start with this particular ID, the tweet ID. And in case you're confused about what the tweet IDs are, let me go to twitter.com and let's see. So here's TF uses Kolkata store session. So this number you see, right? This integer you see here, that is actually the tweet ID. And whatever tweets happen on Twitter after this post will always have an ID greater than this. And this is how this is helping us to filter out the number of tweets that we are pulling in at any time. So once we have done the logger info starting, let's start a loop that while true, we are going to, this script is going to run indefinitely, right? So while true, we are going to check for mentions of a particular user, and we have defined the since ID here, and we have also put in a keyword. So once we define this function, you will see how it's going to work. So before that, we need to define a few helper functions. So I'm going to do that. I'm going to define clean tweet, and I'm going to remove this word, because we are going to pick up tweets which actually contain this word just to make sure that my bot does not start replying to everyone who is mentioning me on Twitter. So I'm going to use this uh, keyword in it, and I have just appended an X to make sure that people who are going through this session only they know what is the magic keyword to trigger it. So yeah, and it's just going to do a very quick removing of certain tokens, removing the numbers and stuff like that, and it's just going to make it a very clean text. You might have to do a lot of it like text cleaning once you're in NLP, and I'm just going to assume that you are aware of this, whatever this is supposed to do. And next, we'll have to create a function for get tweet sentiment. And if you have noticed, then I use this library called text block, and I'll be using text block to get the sentiments of the tweets. And it's up to you if you want to use any library or if you want to create your own. You might even use some APIs like AWS Comprehend. Even you might use the GCP sentiment one. Uh, there's also algorithmia. You might want to use that. So yeah, we'll have this function get tweet sentiment in which we'll just send in the tweet text, and it will do analysis of it after cleaning it, and we will check on the polarity of this particular sentence's sentiment, and if it is positive, then we will make a log of positive, and we will return the string positive. And similarly for neutral, we will return neutral, and for negative, we will return negative. And now we will create the check mentions function. And if you say that it's taking the first API object, which we have put in here, and then it's taking the keyword, our keyword is sendx, and it's taking the sense ID. So it will keep on running, and it will start with one sense ID, and later on it will not start again with that sense ID, but it will keep on updating the sense ID while it's making replies and while the user is making replies from the bot, so that you don't after the loop has started, you don't keep replying to the same tweets which are coming in. So initially, we'll try to set up a loop around that. We will use the TweePy cursor, and we will use it on the API mentions timeline. So API mentions timeline is actually a function which fetches the mentions of the particular user which has been authenticated through that Twitter developer account. And you see that initially we have started with the first sense ID, and later on we will keep on updating this. So we will create a now you might see a short hack here that I have first put all the tweets which I have fetched through the cursor into this mentions list, right? The reason why I do this because when TweetPy fetches all the user mentions, it actually fetches them in the order of recent most first, and I don't want to reply in that sequence. Just a preference that I want to reply to the oldest ones first. For example, if my Twitter bot starts running at say 8 p.m. and there's someone who is going to put in tweets at 8:05, 8:10, and 8:15, I want to reply to the one who put in the tweet at 8:05 first, and then the 8:10, and then the 8:15. But TweetPy actually fetches them in the order of 8:15, 8:10, and 8:05. And that's why to make it to just reverse it, I just put them all into a list, and then I'm going to process that list. And if you see, I have continuously pushed them at the first index, which kind of just reverses the order. And here we have actually updated the new since ID. So we have updated the new since ID, and this is actually our way of saying that we are done with this particular tweet ID, and now we are going to move towards the future. So now this might explain why this part is also needed here, because if we don't have this part, then we will actually reply to the latest tweet first, and we will miss out on the previous two tweets. And then we will do logger info that we have updated the nuisance ID, and we're just going to check if it is a reply to a status, right? We are not going to reply to the tweets which are put in as replies. So if I put in a tweet and someone replies to it, I'm not like my bot is not going to reply to that. It is only going to reply to the tweets which are just put in as original tweets. So it's going to check for the keywords existing in here. So we have just defined one keyword. If there were multiple keywords, it would check for all of them. and it's going to check for all of them whether any of it is in the text of that particular tweet, and if it is, only then it's going to trigger. So first of all, it's going to trigger that it's going to reply to this particular username, and then it's going to, let me just end this function here quickly, and I'll put in a sleep timer as well because I'll talk about that later. And yeah, it will then get the sentiment of that particular tweet, right? So we are just sending the text part of the tweet. We are not sending the entire part. And in the tweet.text, we are actually sending this keyword as well. And this keyword has no meaning. That's why we had to remove this keyword, right? So let's move on forward. And we are going to create a response function as well. And this will be based on the sentiment. It will check the sentiment, whatever is coming in. And according to that sentiment, it will generate a response. So let me define a dictionary of sentiments. And this is just rudimentary replies. These are not smart replies, as in, what you would expect from a chatbot. These are just very rudimentary replies. And for neutral or negative, and it's just going to do a random over them. So whenever we call this function response with a particular sentiment, it's just going to send us any one of these based on the sentiment which we are sending to it, right? So if I'm sending it positive, it might give me any of these three responses. Okay, now coming back here, so we will do an API update status, and we will just say, hey, uh, whatever the screen name. So screen name is the terminology used for the Twitter handle. So whatever their Twitter handle is, we are going to say, hey, that particular person's Twitter handle, comma, and one of our replies, right? So that's going to be fetched by using this response sentiment. Let's make it smaller. And we will reply it to that particular tweet so that we don't end up creating new tweets all the time just to reply to people. And we'll have to send in the tweet metadata so that it also shows up in the replies and mentions of that one tweet. Otherwise, it won't show up there. And yep, we are done with this. So now we have a system by which we'll be replying. And I told you we'll be talking about this later. Right? So why did I enter this logger.info waiting and sleep? Because initially on your Twitter developer account, you will have a very strict limit on the rates at which you can make calls to the API. Another reason why I just said that you need to use a good since ID so that you don't end up hitting that rate very quickly. So in my case, like my account has probably something like 2000 probably tweets, and if I don't set a correct since ID, a lot of tutorials on the internet will tell you that since ID should be set to 1 or like any small value, but please do not do that. It's a very dangerous operation because in my case, I very quickly exceeded the rates and I got blocked for like 2 or 3 times while developing this. You don't want that to happen, right? So, and that's why we have also put a sleep of 1 minute. So our bot is going to check after 1 minute, right? It will check for all the tweets which it has got, and it will determine whether it has to reply to them or not. If it has to, it will make a reply, and then it will go to sleep for 1 minute. So that's how we have our thing ready, and we can probably try running it very quickly. Let me Okay, let's not run it yet. Let me very quickly deploy this to the cloud because we are like 5 minutes from the end of my session. So yeah, let's deploy it to the cloud, right? And that might be very exciting for some of you who are interested in cloud and stuff. So let me go to vulture.com. Vulture.com is just one of the cloud service providers, and it's totally up to you which one you are going to use. Uh, Let me go to deploy. The reason why I am demonstrating virtual here is because you can actually create very small VMs with a very less cost, like even lesser than the ones which you can find on DigitalOcean or probably anywhere else. So I'm going to choose this $3.5 one because it has IPv4 associated with it, and I can do an SSS to it later. I have already added my SSH key, and it is totally up to you to add it or not add it. And I'm going to give it a very quick name, SentiBot. That's it. Server added successfully, and says it's installing. I have some good news. I can earn some additional free credit. That's a very good thing to know. There's some auto articles. I don't want to read them right now. It will take some time to get this deployed. Meanwhile, I can quickly come back and see whether I have some comments. Okay, cool. So if you have questions, you can quickly put them out here because I'm very fine with taking questions during the session. Sometimes while you are working on cloud, it can get boring. Cool. So my server is running, and this its IP. I'll copy it. I might have to get some more details from it, so I'll just go to server details. Oh, it has a password allocated to it. That's cool. Now let me go to SSH root and the IP of that particular cloud instance, and I'll do a yes here. Oh, it's asking me for the password. That's very weird, but let me do that. And I'm in. So the first thing that you want to do on any system whenever you create a VM instance is update, and that's what I'm going to do right now. So after doing the update, we will need an instance of Anaconda or Miniconda running on it. I am going to prefer Miniconda for this because it's smaller and quicker to get started with. You might not always need the entirety of Anaconda. In our case, Miniconda is fine. I'll just copy this link and I'll do a oops, curl hyphen 0 that link. It has downloaded. Yes. Now let me do bash Miniconda, enter Q, yes, enter, and it's installing. So while this is installing, I'm going to take out the repository for whatever I have pushed, and I'm going to copy this. Do I want to init it? Yes. And I'll need to do a quick sourcing of the profile so that I get this base thing here. Now we are into the base environment and we can start installing stuff and like that. So let me do a git clone of the repo. I have clone of the repo now. Let me go to SentiBot. And you see we have all the required files here, right? And there's also this requirement.txt, and if you just do a cat of it, you will see that it just has two requirements, tree and text blob. The reason why we have so less requirements is because Miniconda is kind of filling in for almost everything else. So we are going to do a pip install -r requirements.txt, and it installs stuff. Once it has installed the two libraries that we need, we also still need to download the corpora for text blob. And to do that, we have to just do a cat on the readme. I have already mentioned the command here, so I'm just going to copy it and paste it. And it downloads all the required corporas. And let me clear it. So we are good to start running the code now, but we still do not have a .n on our repository, right? We'll have to create a .n, and I'll create a .n. I have it on my system. I'm going to quickly copy it. There we go. So we have created a .n file, but we have not yet sourced it. So we'll have to source .n, and now we have the environment variable set in our currently running shell. And now we are good to run. bot.py, and it's running. So it tells me that starting with ID, this particular one, it has already got a mention, and that mention did not have a keyword. That's why it has not replied to that mention. But the since ID has been updated to that particular tweet so that it does not consider that tweet again, right? So the next time when after the waiting it is completed, it will be working on new tweets. Let me quickly go and make some tweet to it very quickly. Let me log into the NSCC account, and it will just say, "Hey, Spillion, you did a very good job with the Senti export." And I made that tweet. Let's see if it's going to catch that. We are still waiting. We are waiting for the minute to end. And it caught that, and it had the keyword. That's why it started answering to DAC and SCC. And it determined the tweet sentiment. It got it positive, and it replied with the sentiment positive. Right. So let me go and check what it replied. And hey, DAC and SCC, I feel you're pleased about this, and I think that's something which DSA and SSC was pleased about, though I'm going to delete that tweet later. I'm not supposed to be playing with it, but yeah. So there's this Twitter bot that we have run, and it's working in the wild now. And let me try going back. If you want, you can actually just go ahead and try tweeting to my account. You will have to just use this SentiX thing, right? Make sure you include this keyword, and it will respond to you automatically. So we are kind of done here. You can bring up my slides. Yes. Thank you. So, yep, you can get the code for this particular repo here. You can just go to xp.dev/SentiBot and you will get the code, but you will have to set up your own .env because I've just given the sample file there. So it's up to you. And yeah, this is what you should be doing all the time, right? And even today, the other two sessions which are going to come up, and they're going to be very amazing. You're going to learn a lot of new stuff. And once you have learned the new concepts, apply. Right. So thank you. That's all for my time. And you can contact me on these places. And yeah, if as Rishiraj mentioned, if you are interested in the book, then you will have to go to this URL and fill a very short form, and it's open till tomorrow 12 p.m. So that's it from me. And if you have any questions, then please put them here. Okay, so in case we do not have any questions, I think Rishiraj, you might want to move ahead with today's event. We have some amazing people coming up. Rishiraj, you're on mute.
Thanks, Anubhav Singh, for this lovely session. We went ahead and coded the bot live, and I think that tweet should be okay if it stays in the DSC NSCC account. People can just explore what it's all about. So, thanks for this amazing session. Uh, Now we have Charmi Chokshi with us. She is an machine learning engineer at Shipments. She is also a Google developer expert for machine learning, and let's hear more from her.
Hello, everyone. Hope you are staying safe and enjoying the work from home. Thanks a lot, Rishiraj, for the kind introduction and the whole deeplearning.ai and DSC chapter for inviting me today. So, the title of my session is Decrypting Sequence Models. Today, we are going to see how we can model sequences using deep learning, some of the sequence models such as RNN, LSTM, and so on. So this is what we are going to do today. First of all, we'll learn what is sequence, what are the properties of a sequence, and what are different applications. We'll also see some of the fun demos. After that, we are going to learn about the architecture of some of the sequence models. And finally, nothing is done without coding. So we'll see a couple of applications using models such as recurrent neural network, long short-term memory, and some of the variants of LSTM such as GRU, and so on. And then the session is linked to the next session. The next session, which we are going to learn on machine translation using transformers. So transformers is like the advanced stage of what this session is. So get the basics clear in this session, and then we can move forward with the final session of the day. So let's start that what sequences are. So the formal definition of a sequence is they are collection of elements. Now, if I talk about an English sentence, then that sentence is a collection of words. In that sense, that sentence is a sequence, and the elements which it is made of are the words. Some of the properties of sequences: elements can be repeated. We can have multiple words in the same sentence multiple times. Order matters. If I just give you a jumbled sentence, you would not be able to understand the meaning of it. So, order of the sequence matters. Elements can be repeated. And the final property, sequences can be of variable length. You can generate a sentence which is of just 2 words versus you can have a sentence which is of 10 words or 50 words long. So variability is one of the very important property of sequences. Okay, we understood what is sequence and what are the properties. But why do we care about sequences? Because this sentence itself is a sequence of words. And then these words are a collection of characters. Words itself is a sequence, and collection of words which creates sentences also a sequence. This presentation itself is a sequence of different slides. So sequences are just everywhere. I talked about words and letters. Speech is a collection of signals. It is also a continuous state by state which we are going, and it's a collection of different signals. Videos, they are a collection of images, and then images, they are a collection of pixels. So those combination of pixels which generate images and the combination of images which generates video are also a sequence. Programs which we write every day, which Anubhav showed us in the previous session by creating a live sentiment analysis bot. So in a program, we execute different states of, we execute this code line by line in a sequential manner. If we call some functions, some library functions, if we write some functions by our own, but then we process them, the compiler process them in a sequential manner. That also one of the example of sequences. And if you have ever worked in the field of reinforcement learning, so the decision making which agents has to do being in an environment is also a sequential steps which that agent has to do. In case of a game such as Mario or any of the other games, the agent has to take decision whether I should go forward or backward, up, down, where. So that agent has to take decisions. And that is also one of the examples of sequences. So we understood what sequence is, what are its different applications, and why do sequence matter. So this is a broad category of some of the practical applications of sequence models. You can have just one input and then can expect one output. You can have a single input, a fixed size input, and then you can expect a variable length output, because we understood that sequence model can have variability as one of the properties. So variability here can be in input or in output. If I just talk about a general neural network, we have a predefined image size that you can just have 28 cross 20 by of images as an input, and then in the output you can have just two of the output labels, whether this image is of cat or a dog, whether this uh, sentiment is positive, negative, or neutral. There you have a predefined output category, and then you have a predefined input categories as well. So, but what is very special about sequences, you can have a multiple different kinds of inputs, variable length inputs, and then you can expect variable length output as well. So let's quickly see each one of these, starting with one-to-one. When we expect a fixed size input and a fixed size output. And a classical example of that, which I gave you earlier, is image classification. You can expect some of the images as an input, and then you have a predefined output that only these three can be your output classes. So that's an example of one-to-one models. There are one-to-many as well. When you have a fixed size input and variable size, variable length output, which is a sequence. So do write in the comments that what are the different applications which you can think of, which categorized as one-to-many. Till the time I give you just one example, that image captioning. Here you have an image as an input. An image which is a collection of pixels but is of a fixed size is your input, and then the model architecture and the work of that model is to generate the description of this image. Here giving you an example that this image, if we give this as an input to our model, one of the sentences, one of the description of the image which model has generated is two dogs are in the grass. So here you can see there are 6 words. Here you can see there are more than 6 words, and here they have different number of words. So giving by this example, I'm giving you understanding that how having a fixed size input as an image, we can expect models to generate not fixed size, but a variable sized output in terms of text. And this is a one-to-many image captioning example of one of the models. Do write in the comments what are the other examples you can think of, which can be of music generation, which can be in the field of videos, audios, text, images, and so on. Next is many-to-one. We have sequence as an input, and then we expect fixed size as an output. And the example is sentiment analysis. We can have different number of words as an input, but then in the output we expect 2 or 3 of the classes, that whether this tweet, whether the sentence is a positive, negative, or neutral. So then that becomes a fixed size output, but the input is a sequence. The next one is many-to-many. Given sequence example and get an output as an example, which is the classic example of machine translation. Here you can give an input in any of the language, and the task of the model is to generate the same output in any of the other languages. So the number of characters, the number of words in your input and then in your output can vary. And that's an example of many-to-many. And finally, many-to-many, but when you have a synced sequence. What does that mean? For each and every input sequence, you expect one sequence as an output. Example, video. Video is a combination of images, and then for every images, for every frame of the video, you want some output. In case of image captioning, you give an input as an image, and then you just get one output for that image, that this image is of apple, this image is of dog, etc. Here, we do the same thing, but on video. Video is a collection of frames, and then for each and every frame, we generate one of the output. classes we generate, we rerun the same model on each of these frames. Like here, this is a video classification example that each of the frames is trying to give output as whether the person is kicking a ball or not. So we do this on each and every frames, and which is an example of man-to-many. Okay, so but is sequence modeling a tough task? Like, we have seen most of these applications in production. We do use some of the applications as well. So what is so interesting about this topic is, I guess neural networks can do anything, right? Starting from medicine industry to education to finance to forecasting to automation, machine learning, neural networks, deep learning has application in all of these fields, and they have given a really good results. So these black box, this neural network can do anything, right? So neural networks just period. So most probably sequence can also be modeled using neural network, is what our hypothesis is. But it is not so true, because neural network fails to model the sequences. Why? The property which we discussed of sequences, order matters, variable length, and the third one was we can have repeated elements in your sequence. But variability is not supported by the traditional neural networks. Why? If you have worked with just the hello world of deep learning on the MNIST dataset, creating your first image classification model, you may remember that the input images were of 28 cross 28 cross size. And then in the output, you have predefined 10 classes, whether it's a 0 or 1 or 9. So all the neural networks have this architecture that they have a predefined sequence. If you work on language models, then there also you have a clip limiting. If you have a sentence of, let's say, consisting of 150 words, versus you have average number of words per sentence in your whole data set of 90, then you may use a clip limiting of 90 words per sentence, and then all the words which are coming after the 90th word, you may discard them, or you may make a newer sentences of that. So you may break that sentence. So we have predefined input and output size in case of neural network, which is not the thing which we want in the sequence models, because in sequence model, we want output can be of variable length also. That's why neural network fails to model the sequences. Moreover, if you have ever read the definition of deep neural networks, they would refer that we try to mimic the human brain, the way our human brain works using neuron. They get some input, then they get some output, and then some mathematical functions that are going on inside that is what we are doing in deep learning. But what my understanding is, from all of this definition, that using deep neural network, we are trying to mimic the human brain, is far more ahead than which we are today, because the computation power, the data, the need to train a single neural network is so much than how our brain works. Our brain just works using 20 watts of power. And then if you can see how much data we remember from our childhood till today, and what all processing power we have, our brain has, the memory power, the processing power, the recognition power the brain has, we are still yet to be invent some of the things, discover some of the things, and yet to code a lot of things. So neural networks cannot model sequences. Summary. Okay, this is not the summary of the session. This is just the summary of the sequence part. We understood that sequences are collection of variable lengths where order matters. There are a lot of different applications of sequence models, and not all deep learning models can handle sequence data. So now, if we have enough motivation for the day, so let's start with our very first architecture, recurrent neural network. So we understood that not all deep learning models can handle and model sequences. So what are the models which can handle sequences is what we are going to learn now, starting with recurrent neural network. giving you a simple definition of RNN, the way we can connect two different dots in our memory and then can generate the output is what RNN does. If you are fond of watching movie series or just say movies or serials, then whatever happened in the first episode or whatever happened in the sequence one, you have the ability, our brain has the ability to relate those things to the sequence two or the episode number 50th versus episode number first. We have the power to connect two dots, to connect two different scenarios, and then take a judgment and then understand the present things. So, how do we do that? We can memorize things, right? Whatever I have taught so far to you in my previous slides today, many of you would remember the properties of sequences, the images which I showed, how the layout of this PPT is. You may remember some of the things. So, the remembering power which we have, if we try to give the same thing to neural networks, it becomes RNN. Here, in this diagram, xt is an input to a neural network, A is a neural network, and then there is a state H, which stores the previous information, which stores all of the past words in a sentence written so far, which stores all of the movie scenes seen so far. It stores all of the decisions made so far. And then there is some looping going over here. So, what does that mean? We are giving this hidden state data to our network with this input, and then this has the ability to remember all of the past decisions made so far, all of the past data seen so far. In simple terms, RNN is not really fancy or very difficult to understand network. We want to model sequences using RNN. So we would need sequences in our network as well. And that's what RNNs are. If we just unloop this RNN, they are just sequence of multiple copies of a same neural network. All of them are a single layer network. They have some input and all of them has some hidden state where they store the past data and which keeps on updating step by step. Let's have a closer look at RNN now. All of this network has input, which we show earlier, which have some hidden state, which show we earlier. And then some mathematics going behind it, which gives RNN ability to recognize past movements. And to get these state HT, we will depend on the state HT minus 1. If you want to understand the season number 2 of some series, we expect you to have understanding of season number 1. Or if you are watching directly the season 10th, it might be difficult for you to grasp all of the things. So season 10 is dependent on season 9. 9 is dependent on 8th, and 8th is, and it goes so on, right? So similarly, state HT is dependent on what are all the things were stored in state HT minus 1. HT minus is being dependent on HT minus 2. HT minus 2 is dependent on HT minus 3, and so on. And that's how, using this all the past data stored, we can predict the future data. If we know all the sequences happened so far, then using that chunk of data, we can predict the next data, the next words out of it. Here, to get the state HT, we have an input xt, which is multiplied some weighing parameter. And then we use the information of ht minus 1 with some learning parameter wh again. And because we don't want things to go crazy, we are just limiting it and giving it a 10h function. So the output of ht be in the just limit in the minus 1 to 1. And then finally, let's say giving an example that the keyboard which we use, all of us maybe using Gboard or Swift key or whatever the other keyboard, but we have those 3 different next word predictions on our keyboard, right? So when you keep typing your sentence on every next space, the next 3 word prediction gets changed. So that is developed using RNN. It will use the past information, the past sentence which you have written. It will try to predict, is this any of these three words is your next word. So I have written a sentence like the clouds are in the, and then there will be three different options. And let's say how do we get those three words is based on the softmax. We will be having a vocabulary of all the input words, and then we just want to rank, we just want to give the score of each of these words. uh, Based on whatever the sentence we have seen so far, we will give some probability to each of the next word, and we can have a probability like the next word being a sky is, let's say, 40%. The probability of next word being, let's say, a comb or a remote or TV are, let's say, 5% or 0.02%. So we just want the output probability. So that's why I give this HT and some other learning weight again with the softmax function, and that gives us the probability of next word here in the case of sky. So this is how simply RNN works. To predict the next states, it uses the past states. And how do they handle long-term dependencies? So here we have an quite big paragraph, and our task is to we have given the task to our recurrent neural network to give us what is the capital of the country which we are talking in this paragraph. Or let's say two friends want to meet somewhere, so what is the place where they are gonna meet? So let me just quickly read this paragraph. That finally team was planning to visit France on the final week of his journey. He was quite excited to try the local delicacies and had a lot of recommendations for good restaurants and exhibitions. His first stop was, of course, the capital, where he would meet his long-term friend Jean-Pierre. In order to arrive for breakfast, he took the early 5 a.m. train from London to ... So here, in the very first sentence, we can see that the paragraph is about France, a country, and then where they are gonna meet is the capital of France, which is Paris, right? But if we can see that the country was in the very first sentence, and then the relation of that France to where they are gonna meet, the capital of France, is after so many different sentences and after so many different words. So here is the long-term dependencies. We created RNN to store all of the past data, to store all of the past information. Theoretically, RNN are working in that manner only, to store the past dependencies and then reuse those past dependencies to predict the next predictions or next information, the next audio sequence or the next video frame or the next pixel of the image. But in practical, RNNs fails remembering the long-term dependencies. Here, to get the state data of HT plus 1, if they are dependent on the very initial states, RNN does fail remembering this thing. So this was just the theoretical intuition of why RNNs are not a super cool application to go for, but just giving you a mathematical explanation why RNNs do fail remembering long-term dependencies is due to vanishing and exploding gradients. If you have ever worked in the field of deep learning before, you might know that if the value of a gradient is 0, that means we are giving a flag to that neuron that information stored in this neuron is not super critical, not so important, and we will discard that neuron from learning. We would not learn anything from that layer, from that neurons, if the gradient of that layer is 0. This thing happens in RNN, and that's why they are not good in remembering long-term dependencies. Giving you an example, just forget about the inputs and outputs. Just remember that we have the sequence of those hidden states, H0, H1, HT, and then the learning parameter for each of these states is WH, which we would be multiplying to get the next state value, okay? And how to get HT? We discussed earlier that HT is dependent on HT minus 1 and then multiplication with WH. So HT would be WH into HT minus 1. But we also discussed earlier that HT minus 1 would dependent on HT minus 2. The T minus 2 would be dependent on T minus 3 up to very first state, which was H0. So if we just open up this first equation, HT is equal to WH into HT minus 1, we will get the next equation. Instead of writing HT minus 1, we will write H0, the very first state, and then we will have equation like H0 into WH into H1 into WH into H1 into WH, which is similar writing. WH would come T times and the very first state, because all of these states are dependent on the states seen beforehand. Okay, so now consider this equation, and now if the value of the weight of the learning parameter WH is greater than 1, what would happen? We will multiply that same number with itself over and over again t times, and if the value of t is a bit higher, ht would tends to infinity. We would multiply a value which is more than 1 to itself multiple times. We will get a very large number, and theoretically ht would tends to infinity. And if the wh value is less than 1, if we multiply a very small number to itself multiple times, it will tends to 0. What does that mean? We have a range of 0 to infinity. When wh, the learning parameter, this wh is very far from 1, we have this much bigger range. Our gradients will explode. We cannot have a range something like this. But then some of you may come to me and say that we had multiplied 10h to this function. Don't you remember? So yeah, exactly. Multiplying this 10h would lead us to this range not being from 0 to infinity, but from -1 to 1. But my friend, here that range from 0 to 1 is for ht, the state value, but the gradients would explode or vanish. That's why this is the mathematical explanation of why RNNs have this. One of the cons of RNN of exploding variable gradients is because of the long-term dependencies, because of multiplying that state with itself again and again and again. So before you all start shouting on me that I'm not able to understand anything, what am I doing? Let's have some fun now. If we have clear understanding of RNN and one of its one of the negative side of RNN, which is they are not able to understand the long-term dependencies, so how to go through that difficulty is what we are going to learn next. But before that, let's have some fun. So here I have gathered some of the fun applications for you, and the very first is Sketch RNN. So during the session, I was keep on giving you an example of a sentence. If we want to predict the next word, if we want to create a very similar keyboard of, let's say, SwiftKey or Gboard, where you want users to have a prediction of next 3 words, we will use the data of whatever the sentence we have seen so far. But in case of images, let's see how does they work. So let's say out of all of these different possibilities which I can draw, let me just choose fan. And now it is loading the Sketch RNN model for me. And when I start drawing a fan, the model, I will not draw the whole fan with all of the 3 wings and the middle circle, but I'll just draw one of the parts of that fan. And then let's see how this model complete that drawing by itself by viewing what everything is drawn so far. So now it is saying me that start drawing a fan. So for the first time, I'm just drawing a middle circle of the fan. And now, great, it draw a fan with a stand and all of the spikes inside it. And now let me just draw a ceiling fan, and here I am drawing one of the wings of it and the middle circle. And here the model also understand that this time I want a bigger fan which has a broad wings. So the model understood that this is the centroid of an image and this is the one wing, and now every time it is trying to draw a fan with different wings. Feel free to go through this link and try out all of these different categories drawing yourself. And here there is one more example when we can see how this model is drawing a multiple copies of, here I have selected birds. Here we can also have multiple different things, but let me just draw a face and a beak of the bird. And here they are parallelly drawing a lot of different birds. So from the data sent so far, and from the only small part of the image which I have drawn so far, the model drew 9 different kinds of birds by itself. The first one is, I guess, flying. The second one is just sitting on the floor. And here the eyes of the bird is not present, but here you can see that the model tried to draw an eye as well. And here again, the wings are blowing away, and but there is no eye. So these are like all different kinds of images which you can explore. So we talked that the sketch RNN and the sketch RNN predictor uses some data. So from where this data came, and that's from this quick draw. This is a really very fun application made with Google team as part of the AI experiment project by them. And the applications which I showed you earlier was part of the Magenta project, and which does have a lot of other applications also. So do visit magenta.tensorflow.com by yourself. And here there are a lot of different sketches and a lot of by I mean 50 million drawings of all of these different classes. And let's say if you click on any of those, you can see that what are all different kinds of necklaces this model is being trained. These are all the images which people like you and me have drawn so far and help this neural network to understand how the necklace look alike. So this is a really cool game. And when here you have to when you start the quiz, the model is asking you to draw a wheel, and then if you successfully draw a wheel, you can see here the model is predicting the next word, the prediction of that word. So feel free to explore this thing as well. And the final applications which I want you to understand is the run. Here, this is an application where we can generate music. So we see that image generation, video generation is an example of sequence, but audio generation is also an example of sequence model. And here, when you play this thing, you can hear the sound, how the melodies are being generated. So this is being trained on music RNN. Feel free to explore that as well. I have put links to all of these fun applications here in my slides, which I'll be sharing with you all. Okay, so what we studied so far, what we understood so far. Recurrent neural networks. They have the ability to work with the property of variability of sequences. All of the varying parameter which we see, WH, WT, WF, I didn't tell you how they are came, because there's a lot of mathematics, a lot of differential equations and backpropagation algorithm going behind the scene. This was just a very thorough, not so thorough, but a very light introduction to RNN. but those are really good and powerful models, but they do suffer from vanishing and exploding gradients problem to remember the long-term dependencies. But now we do want to remember long-term dependencies, and LSTM comes to our rescue. Long short-term memory. So if you just forget, I'm making you guys aware how RNN state update was looking like. We had a neural network, then we had some input, a hidden state, and one single 10H layer. This was a RNN state update diagram. And this is how LSTM state update diagram looks like. If we are able to understand this thing, all of the issues which we faced in RNN would get resolved. This diagram looks horrible at a very first glance, but we will chunk this up into different parts. And by end of this session, I assure you that you would understand what everything goes inside LSTM. Starting with one of the difference between RN and LSTM, which is cell state. Here you can see one parallel line going through the whole neural network. So here you can just see in RNN we had a single neural network, and in LSTM in each of the layer we have four different this yellow colored squares which are of neural network layers, and then we have some complex addition and multiplication and some copies of states, and then we are computing some of the vectors and so on. So let's step by step understand this thing. First one is cell state. In case of RNN, we understood that we store past scene information in a state called H. Here, apart from that H, we have another state, which is a C, cell state, where we store long-term dependencies. Okay? And the next difference between RNN and LSTM is gates. In the states, you can see there are some addition and some multiplications are going on. So how do they work? They are due to gates. We will store some of the important information in LSTM states, and then we will discard some of the past informations, because we do not want to again have that vanishing gradient problem and exploding gradient problem. We do not want to store all the information seen so far, or we at the same time don't want everything to be forgotten, everything to be discarded. That's why we will use gates. The way we have activation functions in neural networks, what is the task of an activation function? Whether the information we have, do we want that to pass on to the next layer, pass into the next neuron or not? That's what activation gate would do. If the input is 1, it will be like let everything through, whatever we have so far, pass it to the next layer. And if the output of the activation function is 0, let nothing go through. Don't process this information afterwards. So this is how we have a cell state in LSTM and some of the gates. And there are like 3 different kinds of this gates. And the very first is forgot gate. So if I ask you a question that what did you do on your last birthday, or what was the name of your first school you attended, or let's say what was the last movie you saw, you might remember the answer of these things. But if I ask you that what you had for lunch 3 weeks ago, or what were you wearing on, let's say, 9th of December 2017, these questions you might not remember, right? But our brain has the capacity, the ability to take decisions on what to store for long term and what not to store. Most of the time, all the things which we study are being stored in our brains, but then somehow are gonna brainwashed just before an hour of an exams, right? So giving the same ability to forget something, to remember something, to add and update something to neural networks, to RNN, is what LSTM is all about. It's just the version 2 of RNN. So let's start the first gate, the forgot gate. The task of this function is whatever information we have so far, we want to have a flag output that whether we want this information to be persist in next layers also, or just we want to discard them, and that is being done using this function, the xt, which we show in the case of ironing the input. We'll also use the past state value ht minus 1. We multiply that with some parameters, and then we finally give it to the sigmoid function, which will give us output in the range of 0 and 1, where 0 represents that completely get rid of this thing, we do not want to store this further. While if the output of this forget gate is a 1, which means that completely keeps this thing, store these things that might be a useful thing for future. Okay, the first gate which we have, a forget gate. So now we have a flag that whether to persist something or whether to not. But if we want to forget something, then do we want something to be updated now? Do we want to add something new to those cell states? Is what we are gonna do in the case of input gate. Here we have two different layers. The first one is sigmoid and the next one is tanh. The task of this sigmoid layer is to decide which values to update. If you remember the long-term dependencies example I gave you, there we have a country named France, and then our task was to get the capital of France, which was Paris. Okay, but let's say we have stored that data in our H state and C states in case of LSTM or RNN. But now we have a next paragraph which is on our country, India. And then we are talking about all the different historical places and capital of India, which is Delhi. Okay. So now we do not want to remember the things of country France, but now we want to update those things with country India. We want to update all the places which we had in our network regarding France and Paris. We want it to be updated using India and Delhi, the places of our country. So uh, here we'll do the same thing. We will make decisions that whether we want to discard the information of France or not. And if yes, what all information now we want to store. So the first one is a sigmoid layer, which uses the xt and past h value, and given the sigmoid, if the value is 0, the same thing would happen, that remember something or forget something. And now if we want to update the value of France with India, then we should have a vector of that input value, right? Instead of that France word, we want to store an India word, giving you a brute force example. So here we will get the vector of the candidate values which we want to add to that state again. So the xt, which was the input, in our case it will be India if we want to store that. And then we'll use the past stored value, which was France. We use some weighting parameter, we'll give it to the tanh because we don't want our range to grow from 0 to infinity. And then we have this value. So we understood that, we set the flag, whether we want to forget something or not. If yes, what new thing we want to update. And that's what exactly is being done using this function. The past state value, ct minus 1, we multiply it with forgot get output. If that was 0, we will forget everything. If that is 1, we will remember it. And then if we at all forget the thing, what we want to add. So here we are just doing the addition of the newer value. See the CT, the candidate values of a vector which we want to store next. And then we just multiply it with a weighing parameter, which is like, what is the importance of this thing if you want to store a word India, for how long maybe you want to store, or what's the weightage of this word, or what is the importance of that word. So just a weighing parameter. And that's how the cell update works. And finally, after having a lot of different things, what we want to output exactly. Do we want to output Delhi or some of the places of that, or in case of the example which we show that there are clouds in the sky. So what exactly want to output is very similar to the output of a cell state, which we stored here. Obviously, if we have stored that, we want that to be output. So we just give that to a 10H and then we multiply it with something, and that is the output of our LSTM. And what that something is the sigmoid layer, which decides what part of the cell state we are going to output. We will be having a really big memory, but out of all of those words, out of all of this vocabulary which we have created so far in the memory of a network, what exactly we want to output at this present time, at this present layer, is what being decided using this layer and then multiplying it with the current CT state value, we get the output. So I hope this horrible looking diagram is a bit clear now. There are three different gates which tries to make us understand what to store, what to not store, and how do they work. So this is not the only LSTM models which we use. There are a number of different variants of there. The one is people collection, and all the equations which we show far of forget, get, input, and output, they are very similar. Just the difference that the state value, the previous state value, CT minus 1, we just multiply that with our functions. So this is just an analogy that if apart from all of these inputs, if we give the state value as an input, in some of the cases, in some of the applications, this gives better results as compared to LSTM. So this is one of the variants of it. The next one is like we do not want to forget get and input get as two different entities. What if we couple them? What if we combine them? So in just one network, we will take a decisions that whether we want to forget something and then if we want to add something. So we take decisions that in a single step, which is a couple forget and input gate. And the other variant is GRU, gated recurrent unit. This is one of the very famous and broadly used variants of LSTM nowadays because they gives result in very optimized and faster manner as compared to traditional LSTM. But versus in some of the cases, they may give less accuracy as compared to LSTM. So it is like completely dependent on what applications you have, what data set you have, and we just cannot have an answer to a question that which of all of these different LSTMs, which is the best one. It is like a trial and error approach. There are many different LSTMs as well. Feel free to go through these links where the researchers has found that in some of the applications, even after having vanishing and exploding gradients problems, RNN works better than LSTM. So this is the LSTM summary. We understood how does they work and how do they come over the limitations of RNN, and they are widely used models in sequence modeling, in language modeling, in most of the machine learning research and production tasks. So let's quickly have a small example of how can we code this thing. Deep learning, machine learning is a concept heavy and code lightly feel. Okay, all of this katha which I have done today can be comprised in just 3 to 4 different lines, and then you would have your RNN and LSTM layer. So, but understanding, if you have the understanding of the concepts clearly, then only you can implement and get the intuitions of what to use, when to use, how to use, and how to tune the parameters. So I was keep on using the next word prediction example in my all of the slides. So this is a similar example on the TensorFlow platform in one of the tutorials of using text generation. So here we are just not predicting the next word, but the whole set of words or sentences for that matter. We will just give one single character as an input. Here the input was just a letter Q, and then the model itself generated all of these things. The poetry, the sentences written here are being generated by model itself. Okay, you can see that there are lots of no's over here. So it is not like a very it's not like that it gives the exact good result, the best results, or it has the human level accuracy. But this is a text generation model trained on Shakespeare's data, all of the poems and text they had written. So I'll just quickly go through this example that similar to all the other problems, we just import and do the setup of our libraries and codes. And then here we are using tf.keras. We are using this text file as our input. And there are this many different characters, and this is how the first 250 characters looks like. So this is a data which we are using for our model to get trained for text generation. And here you can see that first citizen, before we proceed any further, hear me speak. So this is like conversation between a first citizen and maybe audience. Okay, so this is one of the sequence which we have as an input in our model. And here is just some data exploration part, that there are 65 unique characters in our model that consist of capital alphabet, second alphabet, and some of the special characters. If we give this text directly to our input to our model, it won't understand because we need to convert this text into numbers. So here we are just vectorizing our text data, and using this zip command, we are just indexing and creating a dictionary, that if we see anywhere letter A in our text, map that to a number 13. If at all we see a letter B, map it to number 14. So giving this dictionary as an mapping to our input data. Here is one example that how a first citizen, the very first sentence of your text data would look alike. It will be something like 1847, 56, and so on. Okay, so these elements, combination of elements, which is a sequence of these numbers, is that it would be input to our model. And then we are just defining some of the parameters, that how long we want to clip our minute, how many epoch we want our model to, and if we want to slice our model or not. And here we are just having this first thing. And now in very beginning, I told you that what is the functionality of this model. If we give that as an input Q, it should print everything after that letter. So to train our model for this functionality, what would we do? The whole this input we had, we create training data by ourselves, that if the input is character F, then everything after F should be in our label set, should be in our output category. So if the input is, let's say, first, okay, first CITIZE, then the output should be from I to N. We want to step by step predict next character. So that is how we are just creating here, creating our training data set for input text. We will just not take the very last character of that sentence, and everything starting from the next character to the end of that line would be our target data set. For an example, first citizen, the whole paragraph for that would be our input, and then we will just clip that F from that input, and it will start from IRST citizen till the end. So here, like in the training, you had YOU, but then in the target, we had this blank space, which was the character which we want to predict after that. So you may go through this slide at your own pace, this example, but okay. So I told you that all of the understanding and summary of the RNN LSTM would be in just 5 to 6 lines. And here what they are. If you have understanding of how GRU works, what kind of loss we want to use there, what kind of optimizer we want to use there, how dense we want our layer to be, then creating a neural network, deep neural network, convolution in neural network, or LSTM is just a child's play, right? So here we are just defining a sequential model for that. The first layer would be embedding of words. We have the dictionary of characters to letters, and then we give this as an input to the GRU network, and then finally we have a dense layer. That's it. This is the first RNN model, and then if we just compile and fit our training data, we can have output of it. So there are really good understanding of this model in this link, which you may go through at your own pace. In my slides, I have also given example of a very basics RNN, how text classification using RNN works, and the final text generation. So final summary of the day. We learn about what sequences are, what are those properties, and modeling them is a hard task. But how can they model them? Using RNN LSTM and the very famous variant of RNN LSTM, which is transformers, is what our next session is going to be about. So if you have an understanding of RNN LSTM, they also have some of the limitations. And in the next session from Souradip, we'll see that how transformers work and how they can be applied in different applications of machine learning and deep learning. These are some of the references which you can use to get better understanding of this thing and the course which we show today. So thanks a lot. I would love to have a couple of questions if you might have regarding this session or anything in general about the field of ML and DL. Do we have any questions? Which would video frame segmentation be under? I don't know if you are okay. So I showed in one of my slides when I was talking about different categories, one-to-one, one-to-many, and so on. So there we understood that video frame segmentation or classification of a video frame is an example of many-to-many class when we have a sequenced input and then we have a sequenced output. So going through that slide again, this is what that thing was. For every single frame of that image, we want output of that frame, that whether in this frame is the person jumping or sitting. So you may have a video of person in one frame kicking off the ball, in the next frame it might catch the ball. So that is how video classification and works. Okay, do we have any other questions? Yogesh Kulkarni is asking that there may not be multiple copies, but the same log getting updated at each time, right? If I understood the question correctly, RNN, if you remember the slide, that if we unroll an RNN, it's a sequence of the same neural network. It's a sequence of connected copies of a same layer again and again and again and again. So it is definitely a collection of combined joined networks. And it is not using the same network again and again. Yeah. If we talk about generating text or captioning video using LSTM, how should we do that? Okay, so a good question that apart from using LSTM or CNN for images, yeah, so Naveen is asking that how can we image captioning works alike, or if I give you an example of a visual question answering system. So that's one of the projects which I was working very recently. In those cases, we give input to our model would be an image and a question that how many dogs are there in this image. That would be the question, and the input would be just like I show here. Okay, so if that was an image captioning, that it may output that there are 2 dogs playing in the grass or in the garden. And if if I have asked the question to my model that how many dogs are there, I expect the answer to be three. How does that work? There are two different things going parallelly. One, we want our model to understand this image, and second, we want our model to understand the sequence, the language, the question of that. For that, to understand the image part, we will definitely use CNN or any of the other um, networks like VGGNet, MobileNet, or any of the image classification model in general can be used. And then to understand the sequence, we use any of the language models like LSTM, transformers, BERT, bidirectional BERT, or other variants of that, because we want our model to understand, first of all, using that image. It will segment that, yeah, I can see three different dogs, but whether this person is asking me if I want to count the number of dogs, or whether the person is asking me where these dogs are playing, so whether I should answer as three dogs or whether I should answer as a garden. So that's why it has to understand the question which I have, a person has asked to the model. And for that, to understand the model, to understand that sequence, or if we use Google search, it is also combined with BERT model. And that's why, like, if I type a question into Google that where is Kolkata located, I can also ask the same question in different manner, that which part of India is Kolkata, or which is the state nearer to Orissa, or what is the standard time of India being calculated, or where sun rises for the very early in which of the states of India. There can be a lot of different questions for a same answer. But how does Google search work to give answer as Kolkata to each of these questions? It's because it can understand the questions, it can understand the language, it can understand the exact of MR country, the meaning of those words, and then order of that words. So if you can model the order of the words, if you can understand that same word repeating multiple times in a same question, in a same sentence, can be of a different meaning. And then if you can model this to have a variable length input or output, um, this is how language modeling and sequence modeling work. Yeah. So to understand the image part, we'll use models like CNN and all. And to understand the language part, we can use transformer and variants of RNN. The next question from Nilagnik is, what is time complexity between GRU versus LSTM? Nice question. Many of the researchers has found that GRU is a simpler version of LSTM, because here, instead of having a forgot get and input get as a two different entity, we combine them. Instead of having a hidden state H and the cell state C, we combine them into a same state. That's why GRUs, or gated recurrent units, have less complexity, or the output of GRUs are in most of the cases are optimized and faster as compared to LSTM. So the time complexity of these models would be lesser in most of the cases as compared to LSTM, because of we are combining so many different steps which were as separate entities in LSTM, but here we are combining. But you can also have this, complexity versus accuracy thing, that many of the cases GRU do not have the similar accuracy as compared to LSTM. In some of the cases, they are performing worse than that. But yeah, time complexity of GRUs is less. Yeah. Thanks, Pratu, for comments. I guess we are running out of time, so maybe I should invite Rishiraj to take on this forward.
Hi, Charmi. That was an amazing session on your part. We really learned a lot, and there is a lot of comments in the comment section.
Okay.
People are really excited for that. So thanks for this session. I'll provide the link to your Twitter profile so that people can ask more questions to you over there.
Yeah,
And
sure.
we'll move ahead with Souradip Chakraborty. Souradip Chakraborty is a data scientist at Walmart, and he's also a Google developer expert for machine learning. So we'll have him next, and let's see what amazing thing he has to share with all of us. Uh, Meanwhile, before he begins, let me remind all of you that there's a post-event survey at the end of this event, filling which you will get 50% off on any deeplearning.ai course in Coursera. So that's it. And now I'll move ahead with Souradip Chakraborty, handing over to you.
Hi, Rishiraj. So, am I audible?
Yes, you're audible.
Yeah, I'll just share my screen and
Yeah, fine.
so can you see it?
Yes, it's visible.
Okay, thank you. So, first of all, thanks for inviting me to speak at the Pi and AI event, which is in collaboration with deeplearning.ai. And I feel very honored and privileged for that. Thanks, Rishiraj and the entire DSC team. And also, I think it was a great sessions by Anubhav and Charmi, and I think they have made my path very easy because it will be very easy for me to explain, and because they have majorly given a brief about how the NLP field has evolved. And I think whoever, like all of you who are with this field, you know that this field has been evolving at a huge rate. So the slope of increase is very high, and so it is very important so that we keep up the pace and we keep updated with what is happening and what is not. So uh, to just mention that my session will be mainly on attention is all you need paper, the transformers. And I'll so the transformers are like when it was started, it was mainly used for explaining from a translation perspective. So from a machine translation perspective, the transformers began and emerged into picture. I will give you a brief introduction of how it emerged, though people have covered it already, but still a very brief introduction of how it had emerged. And then I'll go into the details of the transformer, how is the like how a transformer works and what is the interior detailed mechanism of a transformer. And then I will show you some examples through a code, and also I will give you a an entire repository where the sequence to sequence model is being coded properly, and you can just give an input word, like you can input any language sentence, and you can get any language sentence based on the training set. So that is how the session is planned to be. I will keep it short so that you don't feel bored and leave. So yeah, so to start off my session, I am just to give an introduction. Before that, I am Souradip, currently at Walmart Labs as a data scientist and also a GD in ML. So my topic for today is attention is all you need to paper, the transformers. So just to give you a history and an evolution, how this thing emerged into picture was through the neural machine translation. So machine translation is a sequence to sequence is framed through a sequence to sequence model or a scenario where you have an input sequence and you generate an output sequence. So I saw that one of you asked a question that what happens when you, like for example, in a visual let's say image captioning kind of a scene. So in that situation, what happens is it is also a sequence to sequence scenario. So you encode, so there's an encoder and there's a decoder. So the encoder helps you in encoding the input, so that input can be image, text, video, whatever. So that encoder helps you in encoding the input sequence and giving you let's say a representation of that, and the decoder, and then that representation is fed to the decoder, and also and then decoder outputs are generated at each time step. So for example, if you have an image, for example, in an image captioning scenario, if you have an image of a boy playing a guitar, so there will be the input image will be first encoded through a CNN network, and then the vector goes as an input to the decoder, and slowly it decodes that. It first generates and then goes as an input, it generates a boy, then like that it goes. And how I think Charmi has very well explained that this is how it goes. Now let's come back to the machine translation scenario. So again, machine translation scenario also is a sequence to sequence scenario where we model this entire problem through a sequence to sequence framework. And if you can see, this is the encoding stage and this is the encoder RNN, and this is the decoder RNN. Since here both are text, so we don't have to take any understanding of a CNN RNN or RNN CNN type of an environment. We can simply go with an RNN environment. Now what used to happen is that, let's say this is one sentence and this is another sentence. So this, let's say, ye suis étudiant, and the corresponding translate sentence is I am a student. So what used to happen initially is this entire encoder sequence used to get encoded through one single vector. And by vector, I think people are familiar with that. By vector we mean a series of numbers. Let's say if we have an image, I can represent that image through a series of numbers, and that series of numbers, that entire array of numbers is, let's say, we call here in a simple way as a vector. Okay, so let's say what used to happen is the entire encoder sequence used to be encoded as a vector, and it used to be inputted to a decoder sequence. So for example, generating I, so this entire sequence used to go as an input. For generating am, again this entire sequence of this other language, let's say J, Swiss, étudiant, this used to go as an input. Similarly for A. But you understand one thing, right? That for generating each and every word, the decoder does not need the entire encoding sentence. It needs a overall context, that is true, but it needs to give more focus or more attention to relevant portion of the sequence. So for example, for generating student, I assume that it needs more focus to be given on étudiant, right? And for example, in generating I, it needs to be given it needs to give more focus on J. So that is what the concept of how the concept of attention originated. So it actually what helps the model or helps the decoder in giving relevant focus or giving attention to relevant sequences. So for example, the network learns that for generating student, which of these words are most important, and then it, instead of doing a simple average of 3 vectors, it will do a weighted average, right? So this is how attention learns, and this is how attention originated. And the concept I told just now was a concept by as far as I remember, Badenol. So Badenol was the first, I think one of the premier person to introduce the concept of attention in a sequence to sequence framework. Now I will just quickly explain that now by attention how it works. Because in transformer architecture, as my talk is on transformers, the main attention that is being used is called a self-attention, and a self-attention is a much complex version of the simple attention. So we have to understand the transition, that how from simple attention it went to a self-attention. So let's say in a simple attention, or we call it a visual attention, or let's say global attention if I'm not wrong. So these are the hidden states. Okay, so this H1, H2 and H3. So these are the hidden state. By hidden state, what we mean, as I think you have seen in the previous talk also, that by hidden state is that these are just vector representation of this input sequence. So let's say the input sequence is J, Swiss, étudiant, and the corresponding hidden states are H1, H2, H3. Okay, so now these are the encoder representation. So initially what we used to do is we used to take either a concatenation of H1, H2, H3, or an average for H1, H2, H3, normal average, without giving any relevance to any part. But now the beauty is, now when we are decoding at time step 1, so this is 4 means, like since it is 1, 2, 3, so it is indexed as 4. Don't think any otherwise. This is just decoding at time step 1. So now if you see, decoding at time step 1 is I. So for I, probably the J word will be more important than Swiss and étudiant, right? So what we do is, to understand, so we first take the input, let's say a hidden state of this I. So for I, there will also be a hidden state, right? So that is the decoder hidden state. Then to understand that for this particular decoder hidden state, which of the encoder sequence is more important, what we do is we take a dot product. So if you see this vector, and we take a dot product with H1, with H2 and H3, right? And then the 3 values that we get are 13, 9, 9. Right? So these are called attention scores. So now 1399 is a value, but that gives us a direction, but it cannot tell us that exactly what, because it is not bounded. We need a bounded function so that we can take a decision, right? So what we do is we do a simple softmax. I think like all of you are acquainted with what softmax does. It is just e to the power z by summation of e to the power z. So if you do that, what it will do is it will normalize it. It will make it basically squash it between 0 to 1. Okay. So now what it does is, if you can see that now the scores are squashed. So the first is 0.96, then 0.02, then 0.02. Okay. So based on the softmax scores, what we do is we now average this vector. So instead of a normal blind average, now we are doing it much intelligently using relevant weights for decoding relevant words. Okay, so this is how the attention concept came in, and it was a huge success, to tell you that it actually brought a boom in the field of NLP. So now if there is no NLP paper or work that is being done that is without attention, at least in this field, in this area. So this it has a lot of importance, and once you understand this, it will be very easier for you to understand the later stage, that is self-attention. So just to summarize what happens, you have a decode. So now you need to decode, let's say, the some tth word. So you take the hidden state of that. Okay, you take the hidden state of that, then you take the dot product with all the encoder states to understand that for decoding that particular word, which encoder can be most relevant, and then you weight those encoders and then combine and then give them as an input, so that the decoding is much more meaningful and it's much more, let's say, sensible. So this is how Badonol's attention that we call. Also Luong is another person who proposed something in similar lines. So his also idea was very similar, but instead of, so there were different things. So Badonol suggested for additive attention, Luong suggested for this cosine similarity based attention. So there are different forms of attention. You can easily Google and check that. You can just do Badonol's paper on attention, Luong's paper, you'll get that. So that is the concrete idea. Now let's come back to attention and transformers, and how from LSTM and why from LSTM we transition to this transformer architecture. Now the transformer architecture, to be specific, so what was the problem of LSTM? So one of the major problem of LSTM is that it is inherently sequential in nature. So if we give, let's say, if somebody says that he is a very good boy, so for this generating this, for encoding this entire sentence, or let's say doing an image classification or doing any task, what it will do is it will just see one word at a time. So it will, he goes into the LSTM network, then it understands any hidden state, gets updated, then the hidden, then let's say he is a very good boy, so is goes into the next step, then a boy. So like that, you understand that it goes in a very sequential manner, right? In a very sequential manner. So it is inherently very slow, extremely slow. And people who have trained LSTMs on local machines, you know that if the data set is huge, it will take a huge amount of time, but CNN does not, right? So that is the difference. So now, so this is, since it is exceptionally time consuming, so we need to make some method which can reduce it, or maybe some way paralyze it, right? So that is one point. Another point is that the problem vanishing, because of the problem of vanishing gradients and exploding gradients. So even though RNN's exploding gradients problem gets solved through LSTM, but even for LSTM also, it is very difficult to have long chain memories, because let's say if it is a very long sentence or a long passage, something which is related to a long word, like much before it, it is very difficult to track it and backtrack it. So what happens is we lose the touch, we lose the understanding. So, and especially it can be understood through a very famous problem of NLP in NLP domain, that is co-reference resolution. So co-reference resolution is, for example, let's say he studied well, let's say Ram studied well, and that's why he topped. So this second he is talking about Ram, and this kind of linking. So this is called co-reference, and this is very important in an NLP linguistic domain, and that is how that self-attention originated, or the concept of transformer originated. So this is just to give you a brief introduction, and there are some other problems of LSTM as well, exploding gradient, vanishing gradients, and then it is not bidirectional in nature. So it can only, since it is coming from one sequence, one direction, it is not inherently bidirectional. But then one can always say that, or debate that there are bidirectional LSTM. So yes, that is true that there are bidirectional LSTMs, but yeah, in a normal simple case of LSTM, this is what is the problem. And yeah, and it is like, yes, that is there are, these are the major problems. There are other problems also, you can go through them in some materials. This slide. So the what the self attention does is, it will not give input words one at a time. It will give all the input words parallelly. Okay, it will give all the input words parallelly, and then there will be, so and then it will be learning the relation with each word and all the other words. So for example, it will learn what is the relation between the and all the other words, then animal and all the other words, like animal and the, animal and didn't, animal and t, animal and cross. So all the other words it will learn. So it, let's say if there are 5 words in a sentence, so it will learn a kind, let's say a 5 choose 2 relation it will learn. So for each word it will learn all the other words and how they are related to each other. Okay, and then what it does is, it, the embedding generated, or the vector or the representation generated for that particular word is actually generated through the relationship of it with the other words. Okay, so and the advantage is, it did not be sequential. It does not have to be sequential. It can take any information from any part of the sequence, and this actually can be parallelized, and this is why it was a huge success. The attention is all you need is probably one of the highest cited papers, and if I remember, it was Bengio's paper, and so, and it was exceptional work. So this is how the self attention and transformers concept originated. Now, let me explain you why and how it happens, and what is the mathematics behind it, or what in terms of a dimensionality, what happens. Just to make you understand that if you have simple, very basic concepts of linear algebra, this will be fine. So uh, just simple concepts of matrix multiplication. So if we know, right, if a matrix is of m cross n and a matrix is of n cross l, so then if we multiply a and b, it will be of m cross n cross l, means m cross l. This much information is needed. Okay, so I'll try to explain you what it happens. Now, let's say you have an input sentence which is thinking machines. Just for the simplicity, sake of simplicity, let's assume that it has only 2 words, thinking and machine. So then what we have is, we have an initialized embedding dimension. So let's say x1 and x2 represents the initial vectors. So you have some initial vectors with which you give input to the word. So you need to initialize every word for with a vector, right? I think if you have modeled LSTM or even TF-IDF based model, you ultimately convert each word to a vector, or each sentence to a vector, right? So here, each this x1 and x2 represents the input vector for each of these words, thinking and machines, right? Okay, so now what we do is, now is the main part of self attention, and once you understand this, I think you are almost good to go with understanding transformers, BERT, XLNet, OpenAI. So actually, all of the current state of the art architectures are based on transformers, majority, because there are 2 divisions now again in this domain. So one is a auto-regressive, one is an auto-encoder type. So this BERT and transformer type of models form in the auto-encoder type, and the auto-regressive is the LSTM genre model. But still, I think majority of the successful architectures use transformer as the main thing. And as we all know that BERT, right, the bidirectional encoder representation for transformer, it uses the encoder part of the transformer. So it is very crucial for you to understand that what happens to it. Yeah. So now, as I said, that x1 and x2 be the initialized vectors of the 2 words, thinking and machines, right? Now what happens is, we project this into 3 more vectors. So let's say x1 and x1 gets projected into 3 more vectors. Let's say q1, k1, and v1. So let's say the query, key, and value. So every word in a sequence for modeling a transformer gets projected into 3 vectors. Okay, just remember this for now: query, key, and value. Okay, so for example, if x1 gets projected to q1, k1, v1, x2 gets projected to q2, k2, v2. Okay, by projection I mean, you can always if you know vector and matrix, how they combine. So you can always rotate a vector by a matrix. So or you can project a vector in some other dimension. So let's say if a vector is of d dimensional, you can always project it to p dimensional by using a p cross d matrix. Okay, that is right. So now you have basically this three vectors. So if you can see q1, q2, k1, k2, and v1, v2. Okay, this represents your query key and value vectors. Okay, and these are the matrices. Okay, now let's go back to the next text. Now what you do is, now is the interesting part, how do you capture the similarity between different words is, you take the query of vector 1, okay, or the word 1. You take the query vector of word 1, and then you find a cosine similarity with all the key vectors of all the words, so including its oneself also. So you take a dot product between q1 and k1 is the key vector for thinking, and also q1 and k2, and k2 is the key vector for machines. So then what you do is, so as you can see, you have got two dot products, so 112 and 96, right? Now what you do is you divide by a particular number, so that is not important, but this helps in flow of gradients, but this is not important for this context. Let's say you divide it, and main part is again to have a intuitive understanding. You normalize it and take a softmax. Okay, so to suit it, what is the purpose of taking a softmax? As I said in the before also, during Badonol's attention also, softmax helps in scaling or squashing it in between 0 to 1, so that you can have a very bounded understanding, relative understanding. So now what you do is, once you have this relative importance, that is 0.88 and 0.12, so what you do is, you have now weighted average the values. So you do 0.88 into v1 plus 0.12 into v2, and the resulting vector is the vector or representation vector after self-attention for thinking. Right now you do the same thing for machines. You take its query vector, you query it with k1 and k2, then there will be another this kind of a thing. You will get two more softmax values, then you take an average of their values again, and then that will be the vector for the machines. So now it is shown here. So as you can see that you take a softmax into value. So 0.88 into v1 plus 0.12 into v2. So it has been darkened and lightened so that you can have an understanding that which is more important and all. So now you have now similar. So by combining this v1 weighted v1 and weighted v2 and then adding them, you will get a z1. So z1 is the self-attended representation of the word thinking. And similarly, you do that for Z2 also, and Z2 is the self-attended representation for machines. Okay, so this is how you get a much more robust and meaningful representation, which has incorporated all the, let's say, mutual relations between its neighboring words, or not also neighboring. It can be any word in the entire sequence, right? So now, just to have now I think you are good to understand that what has gone into the self-attention. So just to summarize once again, what happens in self-attention layer is, you give an input, initialize with an input embeddings x1, x2. You project them into three vectors. So q1, k1, v1, q2, k2, v2. Basically, q, k, v projection is being done. Then you take the query vector. So for generating the context vector for thinking, you take its query vector, take a dot product with k1 and k2, and then the weighted softmax scores, you add it to, you multiply with v1 and then v2, and you get a final representation z1. Similarly for z2. So now you have the new representation. So initially you started off with x1, x2. Now you have z1, z2. Okay. So now what happens is, you can see this is the self-attention layer. So you give input as x1, x2, and you have the self-attention layer, and you come with z1, z2. Then what you do is you add residual. So these are residual connection. So residual connection is when you add the input from the previous layer again to the output of the second layer. So what is the main function of that is, okay, let me just show you quickly what is the main function of residual layer. So why residual connections work? So I think this has been explained brilliantly by Andrew Ng in his videos in deeplearning.ai, and that is one of the main reasons that ResNet is such a successful CNN architecture. So what is the main purpose is, if you can see, let's say, though this is a bit complex, but I'll try to explain quickly. So main purpose is, so the main purpose is, if it is, let's say this is a simple deep layer neural network, and let's say this is one hidden state and this is another hidden state, and this is the final activation that you are getting, right? So this is AL plus 2, which indicates the activation after the L plus 2th layer. This is AL. Okay, and you have a lighter network which only gives AL, right? Now, why skip connection is beautiful is, so if you can see, if you just expand it, it will be like W transpose AL plus 1, which is this intermediate layer, and plus BL plus 2, that is fine, plus AL, right? So that if we add skip connection. Now what happens is, if we regularize it, it will make W2 very small, almost zero, based on the importance. So based on, let's say if these two layers are not at all important, it will make W2 as 0, and this activation of AL, if the activation is ReLU, since AL is anyways positive, this will also be positive. So this will be an identity function. So basically it learns an identity map. Since it is able to learn an identity map so well, it indicates that if the network, these two layers, that additional two layers are not very useful, it can simply, it has the capability to simply ignore them and just learn this only, which was useful, right? But if these two layers are useful, it will use that based on the architecture. So this is how the beauty of residual connections are. You can definitely go to this video and see that quickly. And I have for each of my slide, I have given the references from where this picture or these concepts are taken, so that you can quickly go and see. Now coming back to the another part, that is positional encoding. So now you might say, one might ask me that though you are saying that you are parallelizing everything, but how the sequential information gets incorporated? So firstly, the sequential information gets partially incorporated through a representation by this self-attention, because let's say if it's like the boy is very good and that's why he topped in the exam, so you understand that the relationship in between the words will still get captured by this mechanism, because we are doing a dot product and all those things. But the best part is that yes, the best part is we have another additional aspect, which is the positional encoding, which can ensure that the sequential coherence and the sequential relationship is not getting messed up, and it is getting captured. So what we do is, similar to all other embeddings, we also initialize. So like this x1 and x2, these are the initial embeddings of these words. We also give up, like there are positional values. Let's say there are positional values. Excuse me for that. There are positional values which we try to incorporate them. Let's say we project the positional values through some vectors, and those are called positional vectors, and then we add those positional vectors to the input vectors. So basically this, the input vector of thinking and input vector of machines, gets added to those positional vectors, and that gets as an input to the self-attention layer. Now how positional embedding works, again, this positional encoding concept is very complex, and there are a lot of explanations and justifications for that. I will try to explain from my perspective. What happens is this, so generally if you see the BERT paper for transformers, and if you see the BERT paper, what they have done is they have generated sine and cosine values for generating this position. So for example, in this equation, PT represents the tth sentence, and this I represents the ith word. So PTI represents that position of an ith word in a tth sentence. Okay, and they are generated by this function, sine and cosine. So what is the intuition behind this? Let's say, if you see this example where I have just binary encoded this, you can see that it is 000 is 0 can be written by 0001, 1 can be written as 001, then 0010, like that I can encode till 15, right? So I could have done that also, right? Why I didn't do that and do this kind of an architecture? So it is mainly for saving spaces. So you can see that when we generated sine and cosine, it gets alternated, right? Something of that intuition you can get. Now if you see in this pattern, in this binary pattern also, every time you can see that the last digit gets toggled. So it is 0 1, then 0, then 1, 0 1, 0 1, like that, right? And if you see the last two digits, it gets toggled at a different frequency. So 0001 1011, then again 0001 1011. So basically these are like repeating sequence, right? So that is what we are trying to capture, and we'll make the network learn some parameters as well, so that they can capture this sequence also. So this is the positional information. So you can see now you are almost done, and like you are good with how transformer works. So what happens is we give input embeddings of x1 and x2. These are this. Then we add them with the positional vectors, and we ensure that the input embeddings and the positional vectors are projected in the same dimensions, so that they can add it, so that they can be added. Else we cannot add them. As you can see, right, a vector of 10 dimension and a vector of 12 dimension, we cannot add them. So for adding them, we need to project them in the same dimension or ensure they are in same dimension. Then we'll pass through the self-attention block to get Z1, Z2, as I have explained. Then there will be a layer norm which I add, where I add this X and Z because of the residual aspect. And then there are just feed-forward network. We normalize, and then finally we classify, or either we classify or this is the encoder part. Okay, this is the encoder part of the transformer. Now, just one small thing left, that is the decoder part. So as the encoder part, the decoder part also has its own attention layers and multi-head and self-attention. So one thing I have not mentioned is there can be single head attention or multi-head attentions. So multi-head attention basically is just a replica of single head attention, where instead of one QKV vectors, the sentence get projected to multiple QKV vectors. Okay, so but let's, for simplicity, stick to single head self-attention networks. So similarly, decoder also has its single head self-attention network. And also another beautiful part is, since it is mainly originated due to that machine translation aspect, there is an encoder decoder attention as well. So that is called encoder decoder attention, and another is the decoder self attention. So the decoder self attention will work very similarly as encoder self attention. Apart from that while generating, as I think it was mentioned in the previous section, while generating, you cannot see the next part, right? If you are generating, let's say, I am a student, well, after you have generated I, you cannot see I am a student. But while generating am, you can only see I. While generating a, you can only see I am. And while generating student, you can only see I am a. So that is, and so there is a refined version of let's say self-attention which is being used here. That is basically what we do is we give a very high penalty, let's say a -infinity score before the softmax for those positions, and once the softmax is being taken, it makes it to 0. So none of the importance of those, let's say, these positions gets added to the value vector. So that is what happens. And for the encoder decoder attention, what happens is the input is actually the key and value. So basically for the encoder decoder attention, that is also as a type of self attention, just that here the key and value will be of the encoder, and the query will be for the sequence it has seen till now. Means for I, the query will be only the hidden state of I. For am, the query will be a matrix where the first is a first hidden state of I, and am is the first, like, second hidden state. So this is how both this works, but these are pretty similar from the encoder decoder attention that has been used in other contexts. It's just that it penalizes. Otherwise, it is the same self-attention layer. So if you have understood self-attention layer, it won't be a difficulty for you. Yes. Now this is what that I have explained, that what happens in this entire architecture. Attention is all you need, the transformers architecture for a translation mechanism. This is what happens actually. So if you go through this, you will clearly understand that this is the encoder 1, encoder 2. So these are replica of each other. You can use as many encoders as you want and as many decoder networks as you want in a as many self-attention layer as you want in encoder and decoder networks. But let's say here there are 2 encoder networks and I think 2 decoder networks. So what it happens is, this thinking machines, this gets inputted to the first self-attention layer and then feed forward, then normalize, then again it goes to the self-attention layer. All those same things happen with residual connections, and then these are taken as an input to this one. And finally what happens is the decoder learns 2 types of attention. One is a self-attention, where decoder self-attention, where it just learns with its already seen words. Let's say for that previous case, I am a student, let's say we are generating A. The decoder attention will only focus on I and am, and then it will learn. And this is from the decoder self-attention perspective. And from the encoder self-attention perspective, it will learn the relationship between this J, Swiss, etudiant, that is through this key and value vectors, and the relationship between I am. while generating A, and while generating student I am. So this is how it works. And then finally, obviously, you take a brief. And then finally, obviously, you take a very brief, I would say, a concept of transformers or attention or is all you need paper. So you will get all the details in various blogs that I have referred, and also to the attention is all you need paper by Benjo, if I'm not wrong. So these are the main references, and I will, and you can contact me always through this GitHub link. I will just show you a quick implementation now. Yes, so this is a notebook, a Kaggle I have used. So I have not taken any such thing like a very so I have like tried to make it from scratch so that people can understand that how it works. I will be uploading this entire thing and also an example of a sequence to sequence for machine translation in my Git repo and sharing the details, but give me some time for that. But yeah, for simplicity, what we have done, I will just explain through a vector matrix multiplication, so that it's like after even having a basic linear algebra knowledge also you can solve it. So you take the import. Now let's say you generate some text. Okay, let's say the generate some text, and though you literally don't generate, but to have an idea, I have just taken a sequence where the batch size is 32 and let's the max sequence length is 50. So basically, let's say that kind of a thing. Let's say where I am a good boy, and that's why I have, so that length is 50, and then the hidden dimension is, let's say, 128. Okay, so you run that and you get the batch max sequence length and the hidden dimension from it. Okay, now let's say now we do it for a multiple heads, but let's say I make it head 2 as 1 for simplicity. Okay, so what I've done is, as I said, that I project this into query key and value matrices. So if you can see, this x1 is these are the initialize which I have defined, so you can see what happens to it. So yes, so since it is one head only, so this one is because of that. Otherwise it gets projected into this query key value matrix. Okay, this is for the query, this is for the key, this is for the value. Now you reshape it for some operations, and then again you see the shape. And you, what I have done is I have removed this batch size from here and multiplied it with, I removed uh, this head dimension from here and just multiplied with the batch size. That is pretty simple. Now you normal divide it for as I said, that is for the smooth flow of gradients, you divide it, then you see this shape. So this is like 32. So both are batch size is 32, but what you need to do is you need to get a 50 cross 50 matrix, right? Because if it is a, I am a boy, and there, so there should be I am a boy in the row, and there should be I am a boy in the columns, so that you can understand a matrix which will explain that what is the relationship between I am. So basically from this you want a 50 cross 50 matrix. So how to do that? You just transpose this and multiply, as simple as that, right? So this is the dot. If you just do batch wise multiplication, you do queries, that is this, and just you permute, which is like a transpose, and then you see the dot shape, you get a 50 cross 50 matrix. Now, as I said, that once you, these are called attention scores, so you now have the attention scores, but attention scores are not enough. You need to have a normalized or a bounded value, right? That, as I said. So then what you do is you do a softmax, right? You just take a softmax and then you see the shape. The shape remains same, but if you see the values, it will be bounded. So now I assume if you do this, and if I assume this should be okay, this is the sum of the gradients. This is because 50, this is 50. Okay, so that's why. So this is how it will be. And if you take a column by sum, it will be 1. Let me just check that. It's 32 because okay, but it will be okay. So okay, I'm taking the entire thing, so that's why maybe yes. So if you see this will be 1 for like almost 1 for all sequences. So if you see, this is for the first data point, third data point, so all is 1, right? So because we have taken a softmax of it, right? Now what you do is, now you have these values. Now you do, now what, as I said, that after getting the softmax score, you need to do a weighted average of the values, right? So that can again be done through a matrix multiplication. That is the beauty of understanding linear algebra properly. So this is again a batching multiplication of dot and values, and then you just reshape it for your own convenience. So if you reshape it, you will get again a 50 cross 128 dimension. Take the transpose, and yes, you get back your shape, and you do this, and yes, you are good. So you have your own shape. So the input shape, and again the output Z that we showed, remember, in that slide, Z, that is the output of the self-attention that you get, that is 50 cross 128. Now you're good, right? And this is I have broken into pieces, but this is the function. You can just simply blindly apply the function. Now there is like another things that I have shown. You take a layer normalization, which will normalize the embeddings. Then you take a ReLU, and then you apply this self-attention, add the positional embeddings, all those things you do. And another part which is there is these things, the decoder part. So if you do this and you take a, so you, let's say after you take that, so this is queries and this is key. If you do queries and key, then you get the same 50 cross 50 matrix. Then what you do is, this is the another interesting part of decoder. I'll show you what it does. So if you see now the dot matrix, you see that what I was saying, that it gives an infinitely high score for the other values. So let's say while generating one, you can only see one, right? Or just that's the first token, let's say start token. You cannot see the other value. So that's why it has been given by an infinite score, so that after doing softmax, those become 0. So you can see that while seeing the first one, just it is depending on the first one, because you cannot see the other words, right? And then generating this, let's say second one, you can see the first and second, but not the other ones. So it has been done like that. And these values, everything in network learns on itself. So this is the interior, like very in-depth architecture of a transformer, going into its details and seeing its parts. Another thing is the neural machine architecture, machine translation. So if you quickly just see this TensorFlow tutorial, it's an excellent tutorial. You can just go through it. Now that after this video session and after going through the blogs, you have pretty much good confidence and understanding of what happens through it. Then what you do is you simply see this notebook. There are these basic import functions, and then there are some pre-processing Unicode conversions that I have not go through it. Input sentence, and these are the, let's say, translated sentence, and this is the input sentence. Okay, remove the accents, clean the sentences, all this pre-processing you do, tokenize. And then main thing is you convert, these are like converting to bats, like data set, data loader type of thing. So this is the attention architecture that I have explained. Now there's an encoder decoder, and if you go through it quickly, you can see that like how it is translating. So like this has used RNN, but there are, like, I will be soon sharing a material where we'll do translation also through transformers, but I think that would have been too heavy for this session. So I have kept it basics to understanding how the transformer works and how its inherent mechanism works, and what is the basically idea of self-attention, and attention is all you need paper. So that is pretty much all from my side. Please ask me questions, and I think yeah, I'm good to go. Yes. So okay, so the question is, how or in what context is query vector different? Okay, so see, what happens is, now many a times what we do is we have an initial input vector and we project it to multiple vectors, right? But the multiple, now you might say that, see, it is the same input vector, and though it's the same input vector, so how the multiple vectors will be different, because it's the same input vector. But that is not the case, right? The case is, when we have this input vector, right? When we have this input vector and we project it to multiple vectors, the multiple vectors learn the weights, or the, let's say, the values, the activations based on the loss. So this is how it gets learned. So the query vector is main, like the intuition of the query vector is, it will understand that how the query vector of a particular word helps in understanding how it is related to the let's say other words, and for those other words we'll take the key vector, right? So you can think of kind of, let's say, you are questioning someone and they are answering based understanding their question. So the answers are key and the question is the query vector. That is, I think, what the intuition is. Yeah. Is there any question else? I hope people are quite clear with what I've explained then. What is the use of feed-forward mechanism in the encoder section of a transformer? Well, that is a good question, but see, that is like an architectural aspect, because now what has happened as we have seen, right, that it's nothing like we can say that that feed forward has a news or not, but experiments have showed that once we add a feed forward network on that, there has been a significant increase in the accuracy and the performance. So maybe the feed forward network, once we project it to another dense representation, it is capturing some more context, or some more linear combinations, non-linear combinations are happening, which is needed probably out of the self-attention layer. That is not very, there is no theoretical literature you will find on that, but these are like, many things are experimental in nature also, right? We have used different dense layers and seen that it's working or not. So yeah, I guess this is coming from an experiment, and it has shown that it actually enhances the performance by a significant accuracy. Yeah. How do we calculate the attention vector? So yeah, I think the main purpose of the talk was that, but since you are asking that, I'll explain once again that how do we calculate is, we take the input. Let's say there is one word. Let's say in that thinking machines, let's say the vector of the word thinking is 10 dimensional. Okay, it's 10 values you can think, and the vector for each vector, I mean query key and value vector for machines is also 10 dimensional. So everything is 10 dimensions. So what you do is, you take the vector corresponding to query, and you do a dot product with key of thinking and key of machines. So you will understand that this thinking vector should have how much importance given to the representation of thinking itself and also to machines. And based on this importance, you actually average or weighted average their value vectors. So that is how the attention weighted vectors are being computed for each of these words. And if you go through the literature, if you just understand how matrix algebra works, so you can see that it can be represented through a simple matrix product. So that is the beauty. Yeah.
So I guess that's it for the questions. Thank you, Souradip Chakraborty, for this amazing session. The topic that you explained was really a advanced topic, but how simply and clearly and crisply you explained the topic makes it really a good one. Thanks again for attending it. I think our audience loved it. There were many good comments as well. So yeah, that's it for this session. But before, hold on, guys. But before we finish off with this session, I would like to announce two things. First, um, as I already mentioned, there will be a post-event survey at your email ID uh, by deeplearning.ai that you can use for getting a 50% discount on all courses from deeplearning.ai on Coursera. And also, there's another uh, important notice. Tomorrow, there's another event on practical natural language processing, and there, Dipanjan Sarkar, with the data science lead at Applied Materials, will be speaking on the event. It's organized by TensorFlow User Group Kolkata. So make sure you check that event out. I'm providing the link to this event on the screen. It's bit.ly slash practical underscore NLP. So make sure you attend that. And also, before finishing off with this event, there's another question to Souradip Chakraborty.
Yes, yes. Yeah, I'll answer that. So for getting the sentence representation, the best thing to do is take from a BERT if you want to do. So there are two ways. Either you can take the CLS embedding from that, because the CLS embedding encapsulates the entire sentence representation in the most efficient way. So either you can take the CLS embeddings from that, which is again a vector, or what you can do is, you don't take the CLS embedding, take the average of the other token embedding. So for example, let's say if the sentence is, he is a very good boy, take the average of all the token embeddings, he token of is plus token of that, and then average it, and then that is the another way. Or there are much better at things to do, that is go for SBERT or sequence BERT or sentence BERT as they call, sentence level transformers. They give you the most contextual and best representation of sentences. Yeah, thanks.
Thanks. So I guess that is it for this event. So let's call off this event. Have a good night and meet you tomorrow at the TensorFlow user group meet where Dipanjan Sarkar will be a speaker. So have a nice day. Goodbye.